record it and then you guys can watch it. All the people who are not here. Okay, this class is officially dying. Okay, Aiden, you're on. I need your help. I don't have the two ladies I need in my life. Okay, so let's see. Okay, so this one's dead. One is almost dying. Get some more. Hey, all right, Omid, you're on to Aiden, Tate, and Omid need to ask me questions, and I'm going to ask them. So I'm writing this thing here from I equals 1 to n. Okay, what do we have here? Heights of a function times the weights of something, the rectangles under the curve, okay. And if I, so what we really have is, even though it doesn't say that, this implies that there are partitions involved here, right? Now, if I do this, what is this thing equal to? Yes, Aiden, trying to remember your last name, Truvan. Truvan, how do you say it? Truvan, there's 3 syllables there, yes. Very good. So the limit of the summation would be and this is what? This is calculating areas, right? Areas of each rectangle. And when we say to the infinity, we're talking about infinite number of rectangles. And so we're going to get, and this also implies that we are dealing with some kind of closed interval on the x-axis. So the endpoints of that interval would be A and B. And here we could rewrite this as dx. So this is the base of each of the rectangles and ends up being that little differential. And then this is still the height of the function. Okay, if you have this situation, what is, let's see, what's another way to write this bit here, which kind of indicates more of that we have a partition. So I'm going to write that down now. So another way to write this is to say and indicate a tagged partition. So if I write all of this here, which thing in this formulation tells us that the partition the partition of the closed interval on the x-axis is a tagged partition. So notice the difference. Where is the difference, and what indicates that the height, the input for the height, is actually a tag point. Anybody? State the T. The T indicates the tag is involved. So we're dealing with a tag partition, which means the P will have a dot on top of it. All right. So if we have this situation, notice I have not used a limit on it yet, right? This thing then equals, I'm just going to use R for Riemann, not for real numbers. All right. Is that cool? What do you guys think about this? What is this saying? That the thing on the left is this notation stands for anybody? I know we got 4 buddies here. Riemann sum. This is a Riemann sum, which is an approximation. So is this is an approximation. Only when you take the limit of this thing, you get. So this little guy here is in fact the limit. Okay, so when you see an L, now what is another way to represent this? So I'm going to bring an arrow from here. Okay, so we want to, so this indicates that there's a closed interval. This indicates that, what's another way to talk about this square right here in terms of epsilon and delta? If, what is this saying? This is saying that, or this is saying, in fact, if you look at it like this is saying, if you take the limit of this thing, this summation, the limit exists, and if it exists, it's L. This is saying that if the limit of this thing exists, it is L. Okay. How do we express that in epsilon delta value? We need to talk about the base of each of the rectangles, which means we have to have the norm symbols, not the modulus. And this needs to be less than delta. And what do I put in here? Everybody, Tate, help me out. The symbol that will go into here is here somewhere. Not L. Yes, very good. What is this saying? The widest base, the length of the base that is widest, better of all the rectangles under the curve, the base that is the widest better be less than some very small number, delta. If this is the situation, then the second condition we need. So in other words, we can rewrite this whole thing. We are rewriting this whole thing. This whole thing can be expressed like this, or it can be expressed in the delta epsilon version. So then we need, okay, so I'm going to put one modulus symbol here and another one, or absolute value sign. Now we can go with your L, right? So, and then this whole thing should be less than epsilon, very good. And then L goes here, minus. So if this is the exact sum, we could stick this guy in, right? So this is approximate. And then this is exact. And their difference better be less than. So if we are dealing with, what this is saying is that we're dealing with infinite number of rectangles under the curve. If that is the case, or many rectangles under the curve, then if the approximate value of the area under the curve minus the exact area of the curve is less than epsilon, then this exists. So another way to say that if we take the limit of this thing, we'll get the exact area under the curve. Another way to say this top big box is this thing down here. So I am going to use red here. You can either write this or you can write this. In other words, if somebody says that a function is integrable and has a limit L, then we can express it like this. All right, now, all right, and then, okay, going to go right here. Okay, so all of this I did on Friday, and I am redoing all of this again. So I'm going to delete this. Oh, okay, cool. And we have one last class on, well, I'm recording, but Wednesday and then Friday is off, obviously. It's only because it's before fall break and it'll be a ghost town. And I expect only half a person to show up on Friday if I have a half. I've had a class where there was just half a person in the classroom. Well, it's kind of like somebody who didn't have breakfast in the morning. That's half a person. Okay, all right, let's do this. So, oh yeah, keep forgetting. This is the bad one. Trash it. Okay. So here's the statement of the theorem, and it says that if a function belongs to this set called R, comma, this closed interval AB, then the value of the integral is uniquely determined. Okay. STEM people, you guys can read this from the back. If a function belongs to this set, this is a set of functions f that are defined on the closed interval AB, and they are integrable. integrable. If this is the case, then the value of the integral is uniquely determined, which means there can only be one L, right? So over here we have and how do we rewrite this? What is this saying? This is saying that this is saying 1L, this bit here, and this is saying that L exists. Okay, if L exists, how do we write down the math for that? Well, that to prove that L exists. No, we assume it exists. That is a given. L exists. How do we express it? How many different ways did I just show you? We had limit of, right, 2 different ways. And what we're going to do is, if this is true that L exists, and let's say there is only one L, then this is what we need to write, right? So let's do this. We need, what do we need? We need an epsilon. This is our given. And then we need a delta, which is also a positive number. Then we need the norm. This needs to be true. And then, so this is given, and then this exists. Therefore, and then this better be true, and And what do I write here? Anybody remember from the previous whiteboard? The L, right? And then over here, the Riemann sum, right? Very good. And that was F, comma. All right. If the limit exists, then we can write this whole thing. If we have a function over a closed interval AB that is integrable, that is, its integral exists. The integral is this thing here. This is the integral. What is this thing equal to? Just before we go on, this thing is equal to? And this thing, Umid, pay attention. This will help you in your life when you're in dental school. One day some crazy professor will come and say, what about your calculus? If L looks like this, the Riemann sum looks like? Yes? Are we getting close? And then this would be P, and then this would be? So in other words, the integral, the exact sum exists if the exact sum that exists, its difference from the approximate sum better be less than epsilon. If that is the case, then we are good. Now, how do we, now let's look at, so this was all of that. Now, what is the theorem saying? That there is only one L. There's only one integral that that we can calculate if the function is integrable. So how do we prove this theorem? Are you sure? Excuse me. I will pick them up afterwards. So how do we do this? Direct proof or indirect proof? You guys remember from Friday? We've only done one direct proof in this class. Barely done 3 proofs, thanks to you guys. Excuse me. I'm so bitter. Okay. It is. Actually, as I was saying, this class next semester. Oh, maybe. Thank you. So next semester, guess what? I have all these things videotaped. You'll have to watch it at home. And then they will come in and there'll be a quiz that did they watch it or not. It's going to be tough. You guys, this is the last fun class. Yes, there'll be real grades next semester. It is coming. Those poor guys. So the proof is by contradiction. And so we're going to say that not one L exists. Integral is uniquely determined. No, it's not uniquely determined. In fact, we're going to say that there are 2 L's, L prime and L2. So we're saying that there are, for the same function over the x-axis with the closed interval AB, we can actually calculate two what? 2 exact sums of the area. So let's fix this. How do we do this? Folks, help is needed. So epsilon is same for both. If we assume the opposite, right? We're going to assume the opposite of the theorem. And we say, no, it's not just one limit, one exact area under the curve. But in fact, if a function is integrable, it actually has 2 limits, 2 integrals, L1 and L prime. And then in the notation, we need to make changes. So we're saying that this is going to remain the same. And our deltas, are the deltas going to be the same or different? And we're going to go with this partition is going to be finer than this one. Or maybe L double prime will have a finer partition. By finer partition, we mean that the partition that gives us the approximate sum has more rectangles. So one of them will have more rectangles, the other one will have a smaller number of rectangles. It will be less fine. And fine is, according to the class on Friday, an actual term. So we need to indicate, how do we indicate that the deltas are actually also different? If the limit is L prime, then the delta, we could put a prime here. And for the second exact integral, we can make the delta have a double quote to match that. So epsilons are identical. The deltas are going to be different. Okay, so I'm going to draw the L single quote right here, and this is how it's going to look like. Let's say this is our picture. Okay, and this is A and B right here. This is for L prime and then L double prime. We're going to go with this is finer. So how do I show that this one is finer? So L prime has a partition that has only 3 rectangles. And L double prime has this partition is going to be finer. Yes. How many rectangles? Should there be more than 3 or less than 3? Thank you. Very good. So finally, Zara is back from the dead. I know I killed you in this class, but now you have revived. Okay. All right. Which means that is delta prime or delta double prime? Which one is the smaller positive number? Very good. So we have delta prime right here. So whatever the length of this, let's say this is this thing here is and then over here the widest one is this one. Actually, the widest one over there is this guy here, right? So if we look at this, if I make this, if I use this guy over here, will it work? Will this be still smaller than if I took that one and stuck it here? If I put delta prime here, will this still be true? No, because I'm putting a bigger number here. So the width of the widest base will still be smaller than that. What if I took this guy and stuck it here? Will it work? No, because in this case, I put a smaller number than here, and then this might be actually bigger than this smaller width, smaller positive number. Okay, all right. Okay, so is this partition different from this partition? Zara, you're doing so well. Is this partition different from this partition? Because this is finer, has more rectangles than this one. Sophia, are you good? No crying. Let's keep going. Don't cry, for Argentina especially. Yeah, because they have a maniac running it. So what do I need to, I need to fix this. What's wrong here? Very good. Prime is missing, coach prime. And then over here, I need to put what? Which delta should I put here? Double quote, double prime. Okay. What is this saying? Is this the way this is it different from this one? No. Therefore, we need to do 1, put it in blue, and 2. So P1, this is the P1 partition tagged with the dot up there. And then this one is P2. So now we are saying that the partitions are different. In other words, the Riemann sums are different. And now what happens here? Let's do this over here. And we also need and. This needs to be true. Okay, how do we fix this bit here? Excellent. One single quote, and then here 2. What else is wrong with this? Yep. 1 and 2. Okay, so now what's happened is we had a function that was integrable, which means that the area under that function can be calculated over the closed interval AB, because the theorem says integral is uniquely determined, as in the integral value will be just 1, but we're saying no, it's not just 1L, but 2 different exact values. Is that true? Is it possible that the same region under the curve can have 2 exact area values?
No.
Very good. Okay, so which means this is nonsense, right?
Bullshit.
Bullshit, right? Remember the example was that this square here, let's say 2 and 3. What's the area of this rectangle? 6, right? And so we're saying, and that is the exact area of that rectangle. We're also saying that also maybe it's also 5 too. Exactly. That is nonsense. So when we say that this guy here, which is the exact area of the region under the curve, there are actually 2 of these exact sums, that is completely wrong, because we are doing what? Proof by contradiction. We're saying, let's assume there are 2, and let's see how far we go with it. Okay. All right. So next, what happens, folks? Now that we have done this, we want to do this. We want to, the problem is I thought I was not going to have these things are too large. Okay, I could just delete this. So I'm taking this out. If this thing is true, that we have 2 exact areas of the region under the curve, then if I wrote this up, this number should be what? If should be greater than, it needs to be a positive number, right? If these 2 guys are different, this number is 3 and this is 5. 3 minus 5 is minus 2. Absolute under the modulus signs, the absolute, it will be a positive number. In other words, these 2 guys are, in other words, if this is true, then we can say that this is what we're saying is the truth right now. Okay. And so we are going to go next to this thing here. How do we get to that? How can we take one exact the area under the curve, and how can we compare these 2 things? What do we need to make sure that we have changed in order to compare these things? Oh, so the question is, this is the exact area, this is the limit of the integrable function. This is the integral of the integrable function with the partition which only had 3 rectangles. This is the exact area of the function that's partition was finer with more than 3 rectangles. We can't just write that. So we have to make some changes before we can we can write this and check to see if this is a positive number or not. So in order for us to compare, to do this thing, because we want to do a bunch of stuff here, dot, 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 we need to make some changes here. What should we do, folks? And I can obviously cheat. Okay, so what we want to do is we want to use one of these partitions. Okay, which one should I use? Very good, because that's the finer one. And therefore, the delta we will use will also be the smaller one. Okay, so we switch to one partition for both this guy and this guy. It should still be true that they are different, even if we use one partition. Okay, so let's do that so that we can get to this stage here. So then, if we did that, these two guys will change. Okay, so I am going to, so how do we choose between these two guys? We're going to say, so these two will become delta equals, give me the minimum of these two. So this will be our new delta, okay? And then we need to choose one of these guys. So I'm going to write here without 1 or 2. That's the tag, and it's in one of the videos. But since you asked me, I'm going to tell you exactly. So the tag is a point that we choose on the base to use to put it into this guy here. So the tag could be this T right here. And so therefore, it's going to be this height, not this one or this one that will be used. Tag could be this guy. So this will be the height that will go into the f of x. Okay. Yeah. So that's what tag is. You can have this is a very abstract way of thinking about it actually. And it's an easy way to think about this. There are more complicated ways of doing this. So this is the easiest thing that I found. All right. Right now we have 1 and 2. We need to get we need to choose the smaller of these two guys. And so we are going to say that how does he do that? Here we go. And then let this guy be a tagged partition with, so our final exam is on this thingy here, okay? So what's happened here? So this guy here is the same as this guy. Yeah, let the tag partition be, let P dot be the tag partition with this P dot, the norm of it, be less than the delta that we just made. This is only going to be true. So this is the delta that is equal to which one? This one or this one? This one was the finer one with more rectangles, which means this is the number that is necessarily has to be smaller than this one. So if this is the smaller of these two and we stick it here, the partition has to, if this is going to be true, if we chose the smaller one and this is going to remain true, then this partition has to be which one? This one or this one? Yeah, it is 2. But now we don't have to. We're saying let this be equal to a tag partition P dot P2. This is what we just done. This is dot P2, literally. Also, the 2 lines are, I don't know if you were here in that class. There are 2 ways to do this. This is the absolute value signs, and this is called the norm. And the norm says that the length. So the length, the width of the base. So this is saying that the width of any of the partitions, any of the rectangles is less than, if we take the finer partition and the smaller delta, the width of the largest rectangle in the finer partition, which has more rectangles, better be smaller than this, and this is the case then. So now we are ready, because now what's happened is we still have 2L, we still have 2 of these, we have this guy still, and this guy still, but we are underneath the curve. We are still saying we can calculate 2 different integrals, real numbers with different. Let's say this is 17 and this is 13. We still have the area under the curve. Sometimes we say that it's 17 and it's also 13 exact values. But what we've done now is that so this is still true, but we just chose one of the partitions, so we can compare them. And we're calling that partition without the 1. So what's happened is we've kind of gone back to when we started the class and we just had 1 box. There was no 1 here. There was no prime here. There was no prime here, no 1 here. There was no prime here. Okay? All right. So now we can do this business here. In fact, not yet. We have to rewrite these guys, so I have not done that. So I'm going to delete all of this. This is terrible because I'm doing math on one whiteboard thanks to my I don't know how to use that, and then where would it record it and all of that. I should have spent some time on it, but I did not. Okay, how do we rewrite this? First one, so we have, this has 1 here. So the first one is going to look now. So this thing, so this is what we're applying now. So we're applying this guy in the box to the first one. So let's do that in blue. So R function partition, and now the partition is the P2, the finer partition minus, this is still true, and this should be less than epsilon what? And actually, the mistake I did was I forgot to do this shit. If there are two limits, then we can think of 2 limits, then the epsilon better be half the size. The positive number that needs to be greater than the difference between the approximate and the actual area better be half the size. If there were 3, we would divide it by 3. I forgot to do that when I was making changes. We would divide it by 4. That's the trick. So, all right. And then And therefore, there would be 4 of these or 3 of these if there were 3 limits, 3 deltas. So I had forgotten to do that. So this would be, and then this would be, and then what do I put here? I replace this with our new partition, the finer one. So both, this is P2 and this is also P2, but the limits are different. And then this will be still, okay. Now we are ready. So I'm going to delete this. Now we can get to work here. Okay, so we have L prime minus L double prime. This equals to what? What's another way to write this without changing it? Do you see something that's up here that we could introduce without, if we add something and subtract something from this and it doesn't change it, we could, if I added and subtracted L prime, I wouldn't be getting anywhere because we want to do 2 things. We want to apply the triangle inequality rule and then theorem 219. So at this stage, I think I could write it here. So I'm going to write it here. So we have L prime and L double prime. What should I add and subtract here? Given what we have here, what do we do in math usually? Because what is the value of this thing? Do we have a number for this? We don't know, right? We have an exact sum which actually doesn't exist. We have another exact sum which is different from that doesn't exist. But we have these 2 things that say that this thing is less than this number, and this thing, which is also fake, is less than this epsilon divided by 2. So what if we brought these 2 in? So what if I did this? I could add, let's see, what do I do? Make sure. So I'm going to subtract. I'm going to take one of, are these the same now? They're identical approximate sums, right? Because this is the approximate sum of the finer partition. So I'm going to do minus R F comma, and I'm going to add another one of these guys. I added and subtracted the same approximate sum. Therefore, this whole thing is the same as this. No change has happened. Yes? And now we're going to take this thing and so what is, so I'm writing the triangle inequality rule or properties, which is if you have A plus B, in other words, if you have A plus B, you can write this as this whole thing is less than or equal to A modulus A plus modulus B. So the rule is that if you have A plus B, this is less than or equal to A, absolute value of A plus absolute value of B. Let's try this out. If I put in minus 3 plus 5 is going to be less than or equal to minus 3 and 5. This is going to be 8, and this is going to be 2. So this is called the triangle inequality. So here, our first difference is going to be A, and our second difference is our B. So we can replace this thing. We can replace, so this thing is this side. We're going to replace it with RF comma P minus L double prime. And okay, is that good? We just took that, and now we're saying this whole thing is less than this thing down here. Just like this whole thing is less than this thing. Yes. Without this, it would be some, or say the same, exactly. Okay. Just like, because this minus becomes 3 rather than staying minus, negative. And then it would be actually 2 on this side as well. Okay, very good. Now what happens? Now we can say that this actually, I know this number. This is a real number, epsilon divided by 2. So I can replace this by epsilon divided by 2 and this number by epsilon divided by 2. And if I add them, if we add epsilon divided by 2 plus epsilon divided by 2, that is the number that represents this sum here. But this sum is less than. Because this thing is less than that, and this thing is less than that. No, this thing is less than this. This thing is less than this. Therefore, the sum of this, no, let me say that again. Sorry. This thing is smaller than this. This thing is smaller than this. Yeah, so therefore, two small things added. Wrong. Let me try this again. This number is bigger than this. This number is bigger than this. Okay? Or this is smaller than this. This is smaller than this. The sum of these things will remain bigger than these two guys. That's why we drop the equal to. Okay, and we get that. All right, at this stage, if we keep going, we will have, oh shit, we have this. What is this saying? Yes, so that is saying that this number is, because this is what we ended up with, right? And we know if these two exist, that that it's greater than 0. If you have a situation like that, and just to make sure, where did that go? Okay, I just will do it from memory. If you have a situation where you have a number here, if you have a situation like that, that means that if A is if A is between a very small positive number, but still greater than or equal to 0, then this implies that A is actually equal to 0. If we have ended up with a situation where our A is this thing in the middle, it is a positive number, and it is less than a very small, tiny positive. This number can be super, super small. If this is the situation, then this implies that we can equate this to 0. Just like here, if there is a positive A between a very small positive real number, but it's greater than or equal to 0, then we can say that this equals, and this is called the theorem. We did that way early in the semester. Theorem 219. Then, so same here, we can say this is true. which implies that since this is a positive number, we don't really need that. So we can say L1, L prime, L double prime equals 0. And then this thing is equal to which is saying that our assumption that there were two limits, two integrals was not true. We were able to show that they are actually the same. Thank the God. All right. And then on Wednesday, I'm going to go over the poem, unfortunately. But this time I'm going to do a good job and actually focus on that. Thank you, Sophia, for your contributions. Yes, Zara, you too. You were really fantastic today. Umid, you were Umid again. Give my salam to Khalid. Yes. What's that Pakistani